In this video, we will discuss method of Lagrange multipliers, and it is helpful in a way that we already learned how to solve unconstrained optimization problem where we are trying to minimize f of xy, right? And we also saw that, let's say you have f of xy like this, higher value of f of xy makes us unhappy, right? Let's say this is a space of x and y. So higher value of f of xy makes us unhappy. So that's the first intuition, that yeah, how unconstrained can help us, right? So what is a constraint optimization problem, right? So so basically we have a minimization problem in the space of x and y. We want to minimize f of xy subject to the constraint g of xy equal to 0. And what this means we can see in this diagram on the right. So we have to search for all xy in this red curve, which is constraint g of xy equal to 0, and then in this red curve we have to minimize f of xy, right? So that's a constraint optimization problem. And whenever we are inside the curve, we are following the constraints. When we are not inside this red curve, we are not following the constraints, and not following the constraints makes us unhappy. Okay, so what we can do is like redefine a function h of xy which behaves in the following way, and eventually it will make sense, but just follow along for a while. So h of xy is equal to infinity when g of xy is not equal to 0, and it is equal to f of xy whenever g of xy is equal to 0. So now why does it make sense, right? Because whenever h of xy is infinity, it makes us unhappy. Not following the constraint makes us unhappy, really unhappy. So infinity is the max of unhappiness, right? So what we are trying to do here is that whenever we don't follow the constraint, it makes us unhappy, which is basically saying that okay, the value is infinite, the worst thing which can happen. And whenever the constraint is followed, we are happy, we will do the actual thing which we wanted to do anyways, right? So how do we define this kind of h of xy so that we can use the tools of unconstrained optimization here, right? So that's the part. So for that, we'll define something called a Lagrangian, which is L of x, y, and lambda. This lambda is called a Lagrange multiplier. And that is equal to f of xy plus lambda times g of xy, right? And just stay for a while. Now what we can do is we can define h of xy as maximization problem with respect to lambda, L of xy lambda, which is equal to maximization with respect to lambda, f of xy plus lambda times g of xy, right? So if you look at this term in the box, it behaves exactly how we want it to. So whenever g of xy equal to 0, this term will vanish, and this term is not a function of lambda, f of xy, right? So we'll be solving the actual problem whenever g of xy equal to 0. Now when g of xy is not equal to 0, we are maximizing this whole thing, right? And this thing can go as high as it could and reach infinity because it's a maximization thing. So whenever g of xy is not equal to 0, this lambda pulls this product towards infinity, right? So it is behaving in the way in which we want it to behave. Okay, so if I substitute back whatever we just did, right? So this part is the Lagrangian, L of x, y, and lambda. This part was our h of xy right? And basically now we have an unconstrained problem which we can solve through gradient descent, right? So that's helpful. Now let's see the optimality conditions or some properties, right? So first property would be the gradient of Lagrangian with respect to x, y and lambda is equal to 0, right? And this kind of translates to this. This kind of translates to this. Right? So what we can see that this thing, right, which I'm bounding in a box. So this thing actually is a great insight. And what it says is that the tangent of f and the tangent of g are kind of shared. If you look at this diagram on the right, you can see this red curve, and you can see this function f of x. Let's change the color. So you can see this red curve, which is the constraint. You can see this f of xy equal to d1, which is this curve. And what this property says is that when you find the optimal point, the tangent is kind of shared between the curves, right? That's what it is saying. And this is a great insight which will help us later on, right? And if you think about it, why is it so, right? Let's look at this curve, right? Now if you move in this direction, you can improve the function, right? And because this direction will improve the function, you can actually move from x1 y1 here to an x2 y2 here, right? And same thing will keep happening, right? But when you are here, when the tangent is shared, this direction will help you to improve the function, but then you will go out of constraint. So this is kind of the situation where you want to be. You cannot improve any further, right? And that's what this equation says.